Hello Unreal developers, welcome to today's tutorial video where we are building this procedural railway track using blueprints. In this tutorial, I will cover the essentials of working with splines and spline mesh components. I will walk you through how to add materials, troubleshoot common issues, and implement a sophisticated railway track system that's fully customizable through editable properties. So let's jump right in. So let's start by creating a new actor blueprint. Before we open this blueprint, let's first understand how railway tracks are designed by looking into some of the references. So you see in almost every reference, there is a couple of vertical rails connected by an array of horizontal beams. When we look at these curved rails, the first thing that comes to our mind is, of course, the spline component. So in our blueprint, let's add a spline component. So we can easily edit the spline points in the editor, and this is going to give the initial shape to our railway tracks. Now we need to add the rail meshes that can follow this spline path, and for that we need spline mesh component. If you are not familiar with spline mesh component, let me quickly explain. A spline mesh component is a static mesh that deforms and bends along a spline path. That basically means that you can design any straight object. For example, you can design any cylindrical or cuboidal mesh and then use it as a spline mesh component to bend and follow any curved path. Here I'm going to introduce you to my plugin Procedural Vortex tunnel. It is a perfect example of advanced use case of the spline mesh component, featuring a variety of different types of static meshes seamlessly aligned along a spline to create the vortex outline. If you are interested in this product, it is currently available in the Unreal Marketplace, so please check it out. The link is given in the description. Alright, so in our railway blueprint, in the construction script, let's add a spline mesh component. We also need to create a variable that is going to hold the reference to the static mesh that we want as our vertical rail mesh. So this will be an editable property. We are going to add a cylinder mesh as the default value. Let me go over to the static mesh editor for this mesh and select the wireframe mode. That will give me a fair idea of how this mesh has been created, so that if you want to design your custom rail mesh, then you need to keep this reference in mind. Now to make this spline mesh component bend along the spline, we need a for loop. Here I will get a reference to the source spline because the index of the for loop is going to start from 0 till the number of spline points -1. Let me assign a local variable to it. This will hold the reference to the spline mesh component of the current iteration of the for loop. Now we need to call the set start and end function that will set the start and end position and tangent of the spline mesh component. Now I will get a reference to the spline again. and I will call this function get location and tangent at spline point. So the current spline point is also going to be the for loop index. So I will just add it over here. And I also need the location and tangent for the next point. For that, I will duplicate this function and I will set the index as the next index of the current one. Now I will connect the respective nodes. Let's check this out. Okay, so it is not looking right. That's because the orientation of the mesh is wrong. So I will select the function add spline mesh component and set the forward axis to Z. That will orient it correctly. Now we see this issue that it is too sharp at the area where the spline is bent, and that is not exactly what we are looking for. The reason behind this is there is too much distance between the two spline points and the mesh is being stretched beyond its actual dimension. We can easily fix that by changing our logic. So currently we are iterating by the number of points, but we can also iterate based on the mesh dimension itself. And instead of getting the location at spline point, we can get the location at a given distance along the spline. So if you look into the static mesh itself and hover over it, you will see the approx size, which for this particular mesh is 200 by 200 by 200. But when you're designing a custom mesh or assigning a different mesh, then its dimension can be different. So we can use the variable reference to get the actual dimension. We need the get bounds and get the box sphere bounds out of it, which gives me the box extent. So we only need the Z axis because our forward axis is Z. We can also set the forward axis as an editable property. So this function set forward axis is going to set the forward axis of the spline mesh component. So I will promote this to a variable. And set its default value as Z. Here we can use the switch function to switch among the multiple axes. So we need to create a float variable that will store the dimension in the corresponding axis. Okay, so I think setting a value from the switch statement is going to be a little inconvenient with multiple execution nodes here. So a better function is going to be a select function, which will take the forward axis variable as a wildcard, and it will select the respective axis value. I'm going to add a sequence node here. I'm going to calculate the dimension first, and then I'm going to run the for loop. Now I will call the function getSplineLength. That is going to get the entire length of the spline, and I will divide that with our dimension, and that will give me the number of spline meshes that we need to actually generate. This will make the meshes not getting stretched because they will occupy only the size of the dimensions. Now we need to calculate the current as well as the next distance the spline has traveled in the current iteration of the for loop, because that's how we are going to get the start and end position of our current spline mesh. And that can be done by multiplying the current index with the dimension variable. So the very first mesh is going to start from 0 distance, and the next mesh is going to start from the distance equal to the dimension of the mesh, and this will continue. We now got the current distance and the next distance, and we will use them in the function get location at distance along spline. Here we also need get tangent at distance along spline. Okay, so let me connect the respective nodes. Alright, so I think this will work now. So let's take a look. Yeah, this looks absolutely perfect. I mean, I couldn't have asked a more perfect result than this. You can see the spline meshes are nicely deforming with the spline curves, and there is almost no hard edges that I can see. The mesh looks totally smooth. That's also because a lot of meshes are generated this time. Next, I'm going to set up the material for it. I will just add a variable that is going to hold the reference to our material for the vertical rail. So the variable type is going to be material interface. Now I can call the function set material. So I'm going to choose a default material. Now I can select any material from the details panel and it's going to get applied. Okay, so here I can see a little bit of tiling issue. So I want to customize the tiling so that it does not look stretched. For that, I need to go inside the material and I will set the customized UV. If the customized UV node is not available for you, you can simply search for the customized UV here. And in num customized UV, you can set a value to anything other than 0. So the first customized UV is going to be your default UV itself. The customized UV 0 by default is the texture coordinate node itself. But here I will multiply the texture coordinate with the append node. And here I'm going to define two scalar parameters representing each of the u and the v coordinates respectively. And I will be able to modify them from the material instance. Alright, so now let's create a material instance. Here you can see I am easily able to manipulate the tiling of the material by controlling these two parameters. Pretty cool, right? Instead of having the mesh dimension determine the number of meshes that can be generated, I want to have a custom variable called mesh length that is going to determine the length of your spline mesh. So here I don't want to set the mesh length because the mesh length is going to be an editable property. I am still setting the dimension variable. I may find its usefulness later, but right now the mesh length is going to be used everywhere else. So I will set its default value to something like 200. So here you can see I can adjust the mesh length. And if the mesh length is very large, then the meshes are going to get weird again. That's also because for larger mesh length, lesser number of meshes are going to get generated. And we also see an issue over here, which is the tiling issue. If the mesh length is different than the actual mesh dimension, then the stretching of the material is still going to be there. But we can fix that with a dynamic material instance. So basically we need to calculate the tile y parameter of the material instance dynamically. So first let me create a variable called tile y, which is going to hold our default tile value. Let's make its default value 1. Now I will get the material reference and call the function create dynamic material instance. I'm going to set its scalar parameter value. The parameter name is going to be tile y. To calculate its value, I will drag the variable dimension along spline and the mesh length, and I will also need the tile y variable. So I will divide the mesh length with the dimension and then multiply it with the tile y. Okay, so now as you can see, I am able to control the tiling with the tile y variable. On top of that, when I am changing the mesh length, the tiling is not getting affected, which is exactly what I was looking for. Now I want to have a control of setting the scale of the mesh. So for that I will call two functions, set start scale and set end scale. So I'm promoting this as a vector 2D variable that we are going to define from the editor. And I'm adding another float variable to control the scale uniformly. Alright, so now I can set the thickness of the spline mesh component by tweaking this global scale parameter. Perfect. Now that we understood the fundamentals of spline and spline mesh component, it is time for us to start creating our rail track. And for the rail track, we can't set the spline mesh exactly along the spline because there are two vertical rails separated by a specified distance from each other and running parallelly. Let's first define a few local variables to store the location and tangent for the start and end distance respectively. Now I need to calculate the start and end positions of the current spline mesh. For that, first I need to obtain the perpendicular direction of the current spline location. That can be achieved by a cross product between the spline tangent and the spline up vector. Now I need to create a float variable to adjust the vertical distance between the two rails. So each of the vertical rail is going to be at a distance half of the total vertical distance from the spline. So I will divide the vertical distance by 2. Since there are going to be 2 vertical rails, I need to add another for loop here that will run only twice. Here I will add a select node. The index wildcard is going to be the index of this for loop, and if the for loop value is 0, then the option 0 is going to be 1, or else it is going to be -1. The outcome of this is going to be used to determine if the rail is on the left side or on the right side. So I will promote this to a variable. Here I will multiply the distance with this sign value and then multiply it with the direction and then add the result with the start location of the spline to get the final start position. I will do the same for the end position as well. The start and end tangent will be the same. Nice. We now got the result that we are looking for. So now it is time to create the horizontal beams. But before that, let's spend some time organizing this blueprint, rearranging the nodes, commenting out so that it's easier for us to understand what is going on. This is why I am not quite fond of creating an entire functionality within blueprint. It is much easier for me to use a combination of both C++ and blueprint, and typically I would be using C++ for all the base functionalities and use blueprints for maybe some smaller tasks and customizing the editable properties. I decided to make this in Blueprint just for the sake of this tutorial, and if I get enough likes from you guys, then that will really motivate me to make another tutorial where I am doing this entirely in C++. Alright, playtime is over, so let's get back to work. To generate a series of horizontal rails, I first need to declare a variable that will be used to control the distance between the rails. Now we are going to use this distance to calculate the number of horizontal meshes to be generated. We also need a for loop over here. Inside the for loop, I will add a static mesh component. I need another variable that is going to hold a reference to the horizontal rail mesh. The default mesh can be just a simple cube. Now I need to set its relative location and rotation. Calculating its location is going to be very simple. It is just going to be the location at the current distance along the spline. Now we need to calculate the distance, which is basically the horizontal rail distance multiplied by the current index of the for loop. Okay, so lot of meshes have spawned. This is not exactly the desired outcome, but this is happening just because of the scale factor. So we are going to set the relative scale of the mesh. To accurately calculate the scale, I first need the local bounds of the mesh component. And then I will declare a variable that will hold the dimension of the horizontal mesh and is going to be an editable property. So the relative scale is going to be horizontal rail dimension divided by the actual mesh dimension. Okay, first of all, the orientation is not right. And secondly, we also need to increase the scale. So now we need to set the rotation of the mesh. And for that, we need to use the function get direction at distance along spline, which is going to give us the direction vector. And from that, we can easily get the rotation by calling the function make rot from x. All right, so as we can see, the horizontal rails are now correctly aligned. We can increase the Z offset for the vertical rails so that they can be positioned above the horizontal rails. So here we are going to add another vector and we will only modify it Z. So I will use the Z axis value of the horizontal rail dimension. And then I will add it with another variable called vertical Z offset, which I'm going to control from the details panel. So now I am able to manipulate the Z offset of the vertical rail by controlling either the horizontal rail dimension or the vertical rail Z offset parameter. And now let's set up material for the horizontal rails as well. Alright, so our railway track is now completed. I hope you found this tutorial both informative and enjoyable. If you have any feedback or suggestions, please share your thoughts in the comment section below. And if you want access to the project files, they are available on my Patreon page. By becoming a member, you not only gain access to the exclusive contents, but also support me in creating more such tutorials. Moreover, if there is a strong interest from the community, I am open to developing a C++ version of the tutorial. This would not only cover the basics, but also introduce advanced features such as landscape deformation and automatic track generation between 2 points. Your support could make this possible, so let me know if this is something you would like to see. And finally, don't forget to like, share and subscribe to my channel for more such tutorials like this one. I will see you in the next video.